Okay, let's go ahead and get started. Tests were generally quite good. In some cases, adding the 10 bonus points put you over 150. I'm okay with that. Let me briefly discuss the questions, things that came up, common misunderstandings, that sort of thing. So question 1 was draw the truth table for an OR gate, then use only NAND gates. That was generally pretty good. There were a few times where the solutions were a little out of the box, is a good way to put it. And this happened in a lot of circuit problems. And when that happened, you might see me drawing a truth table there, trying to figure out whether your circuit works. There were cases where it worked except for one line, and so I took off some points for that. And I tried to note which line it kind of screwed up on. On number 2, I mean, a lot of people are really confused about demultiplexers in general, and so I want to review that quick. There was just a lot of confusion about this subject. So the idea of a demultiplexer, right, is you've got this input bit coming in, and you've got this select bit coming in, and the purpose of the demultiplexer is to decide where it's going. So it's typically drawn as a trapezoid like this, and so you've got like the input there and the select bit there, and then you've got 2 possible outputs, A and B. And the idea is we're trying to decide which of A or B is receiving that input, and that in turn is determined by this select bit. So there were a lot of people on both this problem and the next problem that were trying to use multiplexers instead of demultiplexers, kind of weird hybrids of multiplexers and demultiplexers and so forth. So especially looking ahead to the final, you want to be super clear in your mind about what a demultiplexer is, okay? Problem 4 was wildly misunderstood by a majority of you. For problem 4, I didn't care about it from the CPU's point of view. I wanted you to explain, how does a circuit work? How does an 8-byte RAM chip work as a circuit? So in other words, I was looking for a discussion of, there are these address bits, and then they feed into the multiplexers and demultiplexers in this way, and this is how the load bits get affected and so forth. I gave some partial credit for answers that were more about CPUs and the like, just because there was a sincere attempt and there was some insight in general. But what I was really looking for was, physically, how does a RAM chip work? 5 and 6 were generally pretty good. Most of you were able to figure out that they were half adders and full adders. And most of you constructed some respectable circuits for them. For the full adder, right, I was really just looking for 2 half adders and an OR gate. I don't quite remember who, but somebody had a very surreal one that had like 3 half adders and about 20 additional gates. Anyway, you know, you should trust me that I'm not going to put an absurd circuit on a written exam. Okay. If I put it on there, please assume that there's an actual sane solution. Okay. Problem 7. These were generally pretty good. The 2's complement. There were some instances where people just missed a couple of key ideas, like for 2's complementing, somebody at one point started with a supposedly positive number that had a 1 all the way over in the left-hand column, meaning that it was negative, and then they got really confused when they tried to complement and it came out positive. And so there were errors like that. There were some arithmetic errors occasionally, but most of those were pretty solid. For 7.2, I was really looking for you to say something like, by doing 2's complement, I can implement addition with subtraction. And most of you got the general gist of that idea. For 8, I was pretty generous on 8. What I really wanted was for you to say, every memory circuit in the computer is wired to the clock. Many of you named a few different kinds of memory circuits, maybe just one, and I tried to be pretty generous on partial credit with that. But what I really wanted was like all of them. For 9, a conditional jump instruction. The number one thing that was missing here that I typically wanted to see was, if we're jumping, we replace the address in the program counter with the jump target. So I saw a lot of good answers that went into detail about how it gets arbitrated, and then it just kind of ended with, and then magically it goes there. I mean, that wasn't a word anybody used, but that was the general sense I got from reading a lot of these answers. I really wanted you to say, bam, you change the program counter. That's how it happens. On 9.2, I was fairly generous here. Any answer that generally talked about how values are getting moved around was fine. What I really wanted to see was some discussion of the instruction bits contain the control bits for the ALU, and that's really how the computation happens. But I wasn't too particular about that. On problem 10, these were generally good. What I was really looking for here was to emphasize a one-to-one relationship between assembly language and machine language instructions. Every assembly language instruction is equivalent to exactly one machine language instruction, and vice versa. That was the number one thing I really wanted to see here, and with an emphasis on the assembly language is more easily human readable, whereas the machine language is directly ones and zeros that can go into a circuit. Somebody had a pretty amusing Venn diagram showing what they had in common and how they differed. Again, I often don't know who wrote what answer because I grade one question at a time. I'm effectively grading most of these anonymously. So then 11 and 12, they were pretty much you got it or you didn't. I mean, there were a few cases where there were some bugs. On 11 in particular, the key insight I wanted you all to have about multiplying by 2 was just to add it back to itself. And most of you got that. There were a few cases where I took off some points because the way you wrote your solution corrupted the inputs. So there were some solutions where it would be like whatever was at location 1 got overwritten in the process of calculating what went at 3. And I took off a point or two for that. You do want to think in terms of preserving the complete semantics of the source program, and that includes stuff that isn't explicitly changed needs to be left alone. But in general, they were actually quite good. And most of the solutions for 12 were correct as well. So overall, yeah, most of you did very, very nicely on this. Yeah, I feel satisfied that in general, you're demonstrating some mastery of the course material thus far. Any general questions on the midterm? Okay, so a few things to talk about on Project 7. So Project 7 is due tomorrow night. You should be well underway with it at this point. I know some of you are because of office hours, things that have come up. There are a few issues I would like to go over with you all. The first issue is that the book on pages 144 through 146 has this design concept for the translator. And what I want to emphasize is that you're welcome to use that design concept, but you are not required to do so. That is, you can design the program however you want. The real purpose of what they suggest for the program structure on pages 144 to 146 is if you have no idea how to get started, here are some ideas that'll work. But in general, there can be a lot of value for figuring out your own design. And what I mean by that is, if it's less mental effort for you to come up with your own design than to actually try to understand what their design is, you should really just go with your own design. There's no need to slavishly follow what they have there. And this was a point of confusion for at least one student. You don't strictly have to follow their design decomposition. You can, it's there as a resource for you, but trust me, I'm not going to be checking your source code to see if you conform precisely to their design. Will I be looking at your source code? Sure. I'll be looking at it because I want to get a general sense of how you went about it and so forth. But and if I see something particularly gratuitous, then that might be an issue. For example, in principle, one way to solve this is to write a program where you see for each test case, you then hand generate and spit out what the assembly code should be for that test case. You can do that. It passes the test cases, and it certainly will not get full credit. So I do want to see, if you've done stuff like that. That said, I honestly think it's more work to do that than to actually do the program correctly. So I'm not actually terribly concerned about it. But in general, I do want to see, how did you go about it? I'm interested in just understanding what your thought processes are and so forth as you tackle the problem. And I do enjoy looking over those. But yeah, you are not required to follow their program structure. Again, it's there. It's meant to assist you. It need not constrain you. Any questions about that? Okay. I'm going to review a few aspects of Project 7 based on what I've been hearing in office hours. But before I begin that, I want to kind of turn it over to you all. Are there any aspects of Project 7 that, based on your work on it, you would like me to review with you?
Okay. I don't know if this is going to be helpful because I haven't done so much. I've only kind of opened the file and sort of parsed the case whether there's multiple files or one file.
Yeah.
But my question that I kind of got stuck on last night is, when you're translating assembly to machine language,
That's
we
right.
knew assembly. We knew exactly what assembly is.
Right.
We just had to write it to assembly. But here, we're translating from VM code to assembly, but I don't think we know VM code. We really haven't gone.
You haven't written any programs in it.
Yeah. So how are we supposed to know that our program is actually exhaustive?
Right. So, one trite answer to that is if it passes the test cases. But a less trite answer is to closely read the chapter and understand what you're being asked to do on this particular assignment. So everything you're doing on this assignment is in one of three categories. You're either doing a push, you are doing a pop, or you are doing math. Okay? So that's everything you're doing for the assignment. Now, with push, you may need to push a constant. Then thinking about push and pop together, you need to be thinking about these memory segments. So just to review, those are local, arg, this, that, static, and pointer. Then for math, you need to be ready to think about add, sub, and an or. And this is kind of one group. And then neg and not, that's a second group. And then EQ, LT, GT, and that's a third group. So this is the assignment right here. If your translator successfully translates all of these instructions, it's correct. Okay. So I think this is a valuable question. I'm glad that you asked it because the assignment can be kind of overwhelming, and I think there's some value in seeing what's the scope of the assignment. What's the scope of it? Now, in all cases, you can directly translate each instruction to a predetermined set of assembly language instructions. This is going to be very, very different in comparison to writing a translator for a high-level language like Java, right? If I write a while loop in Java, it doesn't just sort of immediately translate into a block of VM commands. Like, instead what will happen is it'll translate into a few commands at the start, and then there's this body, and I'll recursively tell it to translate the body as a block of Java code. And then after it's done all of that, then I generate some more stuff. Now, why would I say that for a while loop? Well, at the start of the while loop, I need to check the condition. And if the condition is false, I need to jump till after the whole loop is over. If the condition is true, I fall into the loop. And then when I get to the end, I've got to jump back to the start. So if I just say while, it actually turns into a couple of different pieces of code that get generated in very different places, because the language has this block structure. VM isn't like that, right? Every VM instruction, you can spit out some assembly code and it's done. Now, something that's also come up in office hours is some discussion of, you wind up spitting up quite a lot of assembly code in many cases. Like, each VM instruction can really translate to a lot of different stuff. Something to be careful of here, and this is something I noticed on the exam as well on questions 11 and 12, is be careful with the A register. Be very careful with the A register. Some of what I saw in the exam was that poor A register was being asked to hold a value, and then it would get loaded with a jump target, and then it would ask itself to check its own value to decide whether to jump. Well, that's not going to work because the value supposedly stored there got overwritten when you gave it a jump target. So yeah, be merciful to the A register, and it'll be merciful to you. Seriously. But seriously, yeah, what you're going to be doing is writing small assembly language programs that correspond to each VM instruction. You're going to be writing small programs that correspond to the assembly language instructions. That's effectively what you're doing. Cool. Other questions from you all so far on Project 7? Conceptual things that you already know that you want me to go over. Yes, V.
So do we need to implement like a stack by like having like an empty array or anything along those lines, or do we just think conceptually that it is a stack-like structure?
That's a fantastic question. I'm glad you asked it. It's more the second alternative, and let me describe what we mean by that. When I say you're going to be creating a stack, it's not like data structures where it's like, oh, okay, I'll allocate an array and stuff like that. Why? Because you have no arrays, right? Your code. When I say create a stack, what I mean is create a stack in machine language. And the thing about machine languages is that they have no facilities whatsoever for data abstraction. You will never find a machine language that has classes or even arrays. Instead, you have to, as a mental discipline, mark off where your stack is and how you're maintaining it. There's nothing programmatic that's going to enforce this. So let me review what it means to implement the stack in machine language to make sure we're all as clear as possible on this concept. So if we go to page 141, the book describes how RAM is used. And the first thing I want to emphasize is that this RAM usage is purely a matter of convention and a matter of discipline. You've built the CPU. You know that the CPU has no capability whatsoever to enforce these constraints, right? What does a CPU do? Bits come in, bits go out. The CPU has no insight, no abstraction, no brains, nothing. It's just a dumb little circuit. It's really cool, but it's dumb, right? It's not enforcing anything beyond make sure these electrons go there. So in this memory map then, what we're saying by convention is that 0 to 15 are what we're going to call registers. So these are regions of memory that correspond to extra registers we would typically have on a conventional CPU, right? So on our CPU, we've just got D, A, and the program counter. On a conventional CPU, you'll typically have 16, 32, even 64 registers right there on the CPU. You might be thinking, well, that sure sounds more convenient, and you'd be right. It is. And often what will happen is those registers will often be given designated purposes. To some degree, that's what we're doing with memory locations 0 through 15. Then 16 to 255. This is where static variables are going to be. Importantly for V's question, 256 to 2047, that is going to be our stack. And again, this is pure convention. It's as if we've just decreed, we have an array and it starts at 256 and it ends at 2047. What enforces that? Absolutely nothing. Now, in the context of Java, it's a different question. If I allocate an array in Java, who enforces it? Well, the Java virtual machine enforces it. What does it mean for it to enforce it? What it means is when you write a Java program and you perform an array access operation, so you look up something from an array, you store something in an array, it's going to check to make sure that the index is within the bound you specified when you allocated the array. That was pretty abstract, so let me make it concrete. If I say int x equals new int 10, and then I say x bracket 12 equals 13. So what happens if I do that in Java? All right, I get an exception, an index out of bounds exception. You're right. And the reason I get that is that the Java virtual machine does what's called a bounds check. So it looks at this index and compares it to what's available based on how it was initialized. And if it's out of bounds, it throws an exception. There exist programming languages like the C language that don't do this. You allocate an array, then you give it an index, and then it'll just blindly look it up wherever it is. And that leads to massive security holes in operating systems and unbelievably unrecoverable program bugs. Right. So you have an array go out of bounds, it corrupts some random data structure. The program then just keeps going for like 50 more lines and then crashes mysteriously for no reason. Yeah, no. But of course, that is precisely the scenario we're in now when we're thinking about this region as our stack. Right. There's nothing enforcing it. There's nothing making sure that we don't go out of bounds. We're on the bare metal and it's all by convention. Ultimately, at some point, it just has to be. That said, and this is something I go into in more detail in my operating systems course. I know I say that a lot. It really takes 2 courses worth of stuff to understand all the aspects of this. But a lot of modern OSs use what's called virtual memory. That is, most of you, even your assembly language instructions deal with make-believe memory addresses that get mapped by hardware onto the actual addresses. And so they'll do things like make sure that you stay inside your virtual address sandbox and so forth. And it'll even be checking machine language instructions. Now, you might be wondering, oh, the hardware for that must be complicated, and you'd be right. But some of that does really cool stuff. Like if you run out of RAM, it'll move RAM that's not recently used directly onto the hard disk and just kind of stash it there. In case you ever wondered what swap space is, swap space is space on the hard drive where the operating system parks information that got crowded out of RAM. So then you might be thinking, well, why do I want a lot of swap space? Well, if you're running programs that use a lot of memory, if you've got more swap space, they might run better. So anyway, just kind of a minor detail. So coming back here, then let's look at the rest of it, right? So 2048 to 16383 is the heap. And this is where we're going to store objects and arrays. And then here on up is screen and keyboard. Right. But yeah, especially these first four zones, it's pure convention. So what's this have to do with the stack? Well, specifically what I'm going to do is I'm going to say memory location 0, which is also known as R0 and SP, contains the address of the top of the stack. Now, given all of the push and pop, all of the instructions you're going to be implementing, if you don't get control over the stack, the whole project is toast. Let's just be blunt. You have got to have complete mental understanding of how the stack works. If you don't, the whole project falls completely to pieces, okay? Which is why we're going to go over it again, because I don't want that to happen, okay? So, at the dawn of time, that is, whenever a program starts, regardless of what the first VM instruction is, the very first thing we absolutely positively have to do is set the stack pointer to point to the top of the stack. Now, by itself, if you power on your hardware, what values do you think you're going to have in your memory locations in RAM? So you start from no power, you turn the power on. Nothing, zeros. I mean, I guess whether 0 is nothing is a deeper philosophical question, but yeah, it's all zeros. Now, why is it all zeros? Well, there were no electrons flowing in, so when we think all the way down to the level of the D flip-flop, zeros are all that's there. So zeros then are being output by the D output on the D flip-flop. So everything's a 0, unless we tell it otherwise, right? And what does it mean to tell it otherwise? Well, in this computer, the program counter is again initialized to 0, which means that as the computer begins to operate and the clock pulses, actually even before the clock pulses, the instruction at location 0 in ROM is what is going to determine what the CPU does first. And what I'm suggesting is that when that CPU wakes up, blank slate, looking out at the world, the very first thing it wants to do is stick a 256 as the value at location 0. How many instructions will it take to do that? Instructions? Okay, I heard 3, I heard 1. So V, what's the one instruction that does it? 1 is a little tough. Yeah. What's your 3, Innocent?
It'd be something like at SP, then you can send like D equal to A to get the address, and then at the address M. I don't know how to say it. Maybe I can write it down, but I don't know,
Okay,
it's
we'll
something
come back to that. Andre, what do you got?
At 256, D equals A, and at SP, M equals B.
Okay, so at 256, M equals A, or D equals A? Yeah. And then what would you say?
At SP, M equals B.
So, right. So this would suffice. These 4 instructions would suffice. Just for fun, let's see. Now I'm thinking. I'm wondering, can we do it in 3? No, I think we got to do it in 4. Yeah. And the reason we got to do it in 4 is we have to specify the value. We have to keep it from being overwritten. We have to specify the target, and then we set it up. Right? Yes.
So how do we do something like push constant sum value?
Well, let's think about that, right? What does it mean to push a constant? Let's scroll it. Whoa. Okay. I'm sorry. I hope I don't give anybody motion sickness. So if I'm going to do push constant n, what's the first thing I'm going to do? I need to say something like at, okay, my at sign got very bad. Let's try that again. At n, d equals a, okay? And now what? Oh, go ahead, V. Right. So how am I going to change my stack? Well, do I change my stack pointer or do I store the value? What happens first? What's that? Yeah, exactly. Yeah, I have to store the value first. So a store is always just this stereotyped sequence of 4 instructions, right? I have a value, it goes to D. I have a memory location, the value from D goes to it. So what's that going to look like over here? I've got a value, it's just hanging out in D. Yes?
We need to put it on the stack. And
Yep.
putting it on the stack means pointing to the address of the stack pointer and then adding that value there.
Pointing to the address of the stack pointer. Boy, is that a mouthful. So what's that going to look like to point at the address of the stack pointer?
If you have like a local variable called like SP that keeps that variable, can do like at SP.
Mm-hmm.
Then it could be something like M is equal to D.
So what's this going to do? Is this going to put it on the stack? Yeah, Andre.
It sets the stack pointer to the constant.
So Andre is right. And let's all make sure we understand why he's right. I've put N into D. And now I'm pointing at the memory location of the stack pointer. And I say, I want my stack pointer to be N. Yes, V. What's that?
I jotted down some notes yesterday. So after at SP, it should be AM equals 1.
So there's an interesting a couple of ideas here. It's not quite right. And the reason it's not quite right is that we don't want to increment the stack pointer until we've actually stored our target value. But let's think about the implications of what V has suggested here. She's suggesting look up the value in the stack pointer, and let's assume it's just 256. This is the start of time, right? What this says is have the stack pointer be 257, and while you're at it, also have the address register be 257. So this is a pretty important insight here, which is that because the stack pointer itself contains a pointer, we need to load its value into the A register, right? So let's just review, right? At the stack pointer, I've got a 256. At 256, I ultimately want n to be there, right? So if I want n to be there, I have to make my address register have the value 256. So V, how would we simplify this line of code to disregard incrementing the stack pointer and focus just on the address register? So remember, if you say A equals n plus 1, we're updating 257. A equals A is admittedly funny, but not terribly productive. And I'll give you a hint. I just erased one thing over here. What should I erase over here?
The one.
The 1. Should I erase anything else? So let's look at this instruction, right? I've placed the value n into the D register. Now, the value at location 0 is in the A register. So if I now undertake an instruction that impacts memory, it'll be at this location. So I've just got a couple more instructions to push a constant, right? So what's next? Okay, I got to stop erasing. M equals D. Right, now N is definitely there. But now we got to come back to what V was working on earlier, which is we have to increment the stack pointer. Because if we don't increment the stack pointer, the next time we do a push, it's just going to write over this. We got to increment the stack pointer. So how are we going to increment the stack pointer? Okay. And then what? Bingo, right? So M equals M plus 1, and now this is 257. So that is the kind of code that you're going to have to generate for push constant. Well, what do you think? You think so? You think so? Now, of course, there's no N in the assembly language, right? So a lot of how I want you to think about this is you generating templates of assembly code. So you can even imagine having strings kind of ready to go, just with pieces that you're going to plop into the strings at different times. Yeah. But really, aside from this line, the rest of this is just always going to look exactly like it. So that's pushing a constant. Let's examine this block of assembly code and tease out essential elements that you're going to need over and over and over again, right? So, first thing I want you to pay attention to is this little block right here, right? This is what we would call indirect addressing, right? What makes it indirect? The memory location we need is actually stored in memory somewhere. That makes it indirect. Then over here, We have a memory update. And something really valuable that we're taking advantage of here is the fact that the ALU has incrementing and decrementing instructions. In other words, we don't need to use the A register as a means of getting a one constant in there and adding it and so forth. We can just directly add one or subtract one from any memory location at will. We can do that. Over here, of course, we have load a constant, right? And we're going to be doing that a lot. You've got a constant value. You can stuff it immediately in the A register, but the A register is such a busy place that D is a safer holding cell for it. So putting these pieces together, though, yeah, we can push a constant. Push a constant is one of the simpler operations we're going to do. It takes 7 assembly language instructions. From this, you might infer that some of the other operations we're going to do are going to be more than 7. Some will be fewer, especially like not and negate. Those are pretty simple. But some of them are going to be a lot more. Is the stack making more sense now? Yeah.
Question. Let's say if I wanted to add the two numbers that are on the stack.
That's right.
What we usually do, we pop the first one,
right.
The second one, you add them and you push back the results.
That's right.
In that sense, before I do that calculation, do I need to actually do it on the hand in my high level language and push out the results? Or I need to make sure that ALU does the thing, does the job.
You want the ALU to do the job.
Okay.
And specifically, when you're thinking about having the ALU do arithmetic, you want to do it in the smallest number of instructions that gets you the specified result. So we went ahead and put together the assembly language right here for push constant, because I think that's a nice way to get you all into the feel of what you're going to be doing. That's a fancy way of saying I won't be doing it for anything else, but I'll be happy to sketch out the concepts of what it looks like. So let's begin by thinking about something like neg. If I'm generating code for a neg instruction, the semantics of it are something like the following. Pop a value, negate it, push the negated value onto the stack, right? But we don't actually have to do that much work. And the reason is this. Let's say the stack pointer has a particular value at the start. At the end, did the stack pointer change? No. So my first suggestion is don't change the stack pointer, right? See, what matters is just after you've generated the assembly code, is the memory in the correct state? How you get there doesn't really matter. So it would be fine with me if you do some kind of memory instruction using the ALU to directly change the memory to be negated. So this winds up being one of the smaller bits of assembly code you're going to generate. You should be able to do it in just a few lines. Okay? Now, let's think about what this means for something like add. So add, the stack pointer starts at a particular value. When it's over, what's the stack pointer going to be? So you pop two things, add them, and push the sum on. One less, that's exactly right. It's going to be its old SP minus 1. So you're definitely going to have to pop something here. But you don't actually have to pop both of them. You could imagine just pop the top value, get it into your D register, and then just do the math straight in memory. Right? And so this isn't all that many instructions either. The point being, whenever you think about an instruction that affects the stack, we might talk informally about it in one way, but what really matters is what is the state of memory after the instruction completes. Any set of instructions that gets you to that final legal state is completely acceptable. Okay? Now, of course, when I say gets you to the final legal state, an important thing to emphasize is should only change the things that should be changed. Right? But given that, yeah, you don't really have to pop twice. Yes?
Yeah, so for add, we set A to that -1 to the memory location before. So
That's right, yeah.
A value, and then add that value to the original SP.
To the value that's indirectly addressed by the SP.
Yes.
Yeah.
And that should be how you add two constants together.
Pretty close. I'm not going to put it up here, like I said. We just did one example, really. But I think you've got the right idea. There might be a detail or two that you need to alter, but you've got the right flow in mind. Yeah. So, looking back at the overall scope of the assignment, notice that I put things into some groups here. Add, and, or, and sub all generate the exact same assembly code, except that the ALU operation is different. So again, you can build a string where you get to plug in your ALU operation. Right? Neg and not do the exact same thing, except for the ALU operation. Now, the thing they do is different than these, because these are unary operators as opposed to binary. So they might need their own string. And we're going to talk about these miscreants in a moment. The comparators are very complicated. Coming over here to the memory operations, local arg, this and that are a group. And then there's pointer. Is there another one? Did I forget a segment? I feel like I forgot one. Temp. I did forget a segment. Yeah. Pointer and temp are kind of the same thing. And then static is its own thing. And then, yeah, here are the groups over here. So overall, we've got 1, 2, 3, and then 4, 5, 6, 7, 8, 9 distinct things. Why did I count each of these twice? Well, there's pushing and there's popping. Oh, and constant makes 10. So you've basically got 10 different blocks of assembly code that you're going to need to generate. You work out what's the pattern of assembly code for each of these 10 possibilities. Make it a stereotype string. Of course, you might be able to share some pushing code among all of these and some popping code among all of them as well. So you might have a couple of different strings you're putting together, to get to a certain point. And that's basically the assignment right there. It's just putting those pieces together. Yeah. Yeah.
So the book specifies that our VM should be able to receive either one file or a folder that has multiple files, that has .vm extension.
Not for project 7. For project 8, you're absolutely going to need to do that. So for project 8, you'll need to be able to tell it, here's a folder that contains VM files. Load and translate all of them and generate a single ASM file. And you can certainly set it up this way right now if you want, because you're going to have to do it eventually. But none of the test files for project 7 are going to require that. So even after project 8, you'll need to be able to say to it, here is a single file to translate, or here is a folder with files. And you'll need to make it work in either event. Yeah, good. Other questions so far? I'm going to spend some time reviewing the memory segments once we've exhausted any other questions. Any other questions so far? Yeah, Spencer.
The book says, like, just kind of go into math and then this order. Would you suggest going in that order?
So it's reasonable to, I mean, you got to do push constant before you do anything. Push constant, math, memory, yeah. So specifically, if we review the order of the test cases, so we're on project 7. You'll want to do simple add first. To get simple add working, you need push constant and add. And that's it. I think once you hit stack test, you start needing the memory segments. But if you just do simple add first, you'll get a lot of essential ideas down. Once you have add going, most of the rest of the math is pretty easy. LT, GT, EQ are another story, which I'll review again in a moment. Yeah, but I would definitely start with push constant and add. Good. Other questions so far before I talk more about these and these? Okay. I was going to talk about this next, but actually let me hit this first, then I'll go to these. So EQ, LT, GT. Here's the issue with these. These cannot be done as simple ALU operations. So you might remember that the ALU has flags that correspond to these values, and we have jump instructions that make use of them. The trick in the VM language is that these are going to take their 2 arguments and then produce one of 2 possible values. Those 2 possible values are -1 and 0. -1 means it's true, and 0 means it's false. -1 may seem kind of arbitrary, but it's actually very valuable, because what's a -1 going to be in binary? All ones. So by making true all ones, it means that if I do a not on -1, it means I get a 0, right? And if I do a not on 0, it means I get a -1. So that's really valuable. What's also valuable about these instructions is that they directly compare 2 values. You might remember that at the machine language level, all you can ever really do is compare to 0. What these instructions do is they compare 2 values to each other. Now to do that, you're going to have to subtract them. So the sequence of events here is first subtract, you're going to do the subtraction x minus y, where x is kind of one level below the top of the stack and y is what's on top of the stack. And then the next thing you're going to have to do is generate a jump instruction using the correct condition. So, if you're doing a GT, you'll generate a JGT, and if you're doing an LT, you'll generate a JLT, and EQ, generate a JEQ. Okay? So let's say the jump succeeds, and then you push a -1 onto the stack. If the jump fails, push a 0 onto the stack. And so here you might even generate some of your own code that you've already come up with for pushing a constant. Now, do you all think there's anything tricky about pushing a -1? What might be tricky about pushing a -1? Let's think about this. What's the number of bits in a value on our CPU? 16-bit value. If I use an at instruction, how many bits do I get there? How many? So can I ever at a negative value? No. That's why I brought this up. We have to push a -1. We can't at a -1. So how do you all think we can get a -1 using our ALU? Anybody remember? Can we just use the ALU to give us a -1? How does that work in a sense?
You sort of, yeah, like you zero everything. Like you take the incoming value, you zero it, and then you flip it, and then you add 1 to it.
You don't even need to add 1, right? If you have all zeros and you use a not, what do you get? So if the ALU can do that directly, right, then what I'm suggesting is make the ALU do the hard work. Yeah. What I'm saying to avoid is don't try to use an at instruction. Use an ALU instruction to do this. To get your -1. Yeah, that's all. And remember that your ALU has the power to do that. In any event, yeah, this is what you're going to have to do for those. These are going to be probably your largest instructions. And you're going to have to be careful to do stuff like once you've jumped and pushed your -1, you have to jump past the other thing and so forth. Yeah.
You know, usually when you do a jump in assembly, we need to have like a label of where we're going to jump to.
Oh, yeah.
How are we going to know what label to use?
That's a great question. What do you all think? How are you going to know what label to use? Is anybody going to tell you? No, nobody's going to tell you. So let's talk about this. How do you make up a label to be a suitable jump target? Ensuring that the label is unique. Yeah, Spencer.
Can you use the stack pointer?
No. Yeah, Andre. Just make a counter. Yeah. So what you can do is have a counter for every unique jump target you have to generate. It can't start with a number, so you just come up with some prefix like jump or something. And then the first time you need a jump target, you generate like jump 1. And then the next time it's jump 2. And then maybe after that it'll be jump 3 or jump 4. That's how you do it.
Okay.
Yeah.
Maybe a follow-up question to that.
Yeah.
You know, after jumping, you have like a block of code specified somewhere that says jump 3, do this.
That's right.
Like, I'm not kind of thinking how this code is going to take care of that, you know? How it's going to create that block of code. It can sort of create a jump statement that goes there, but creating that block of code, how is that going to work?
You're going to do it, right? So you've got one block to generate if your jump succeeds, And when that ends, it just moves on to the next rest of the program.
Yes.
If your jump fails, you have to push the 0, and then you have to jump past this. Right? So let's think about what the control flow is going to look like. So the control flow is something like this. You're going to subtract. You're going to jump. And then you're going to have the fail code. And then jump past the success code. Then you're going to have a label. Jump N, say. And then you're going to have the success code. Then you're going to have a label like done N. Or maybe it's just, I don't know. Doesn't have to be that complicated. Could be jump N plus 1, right? Or whatever. So that's the structure of what you have to generate. You get that structure right, there shouldn't be a problem. Again, remembering every VM instruction just gives us a single unified block of assembly code, but then just appears sequentially in order. Yeah, V.
When you interpret one line of VM code into ASM, how do we keep that from, it'll be like a big block of ASM.
Mhm.
So how do we keep that from overriding the next few lines?
Oh, I see what you mean. As you read in each line of VM, your output file, you send as much ASM as you want. So keep in mind that the file pointer for your input file and the file pointer for your output file are different pointers, right? So you might be 5 lines in your input file and 50 lines into your output file, and there's no problem there. Where the problem would be is if you were trying to write right back into your source file as you were going, which no, just no. Good. All right. So we just got 10 minutes left. I'm going to review now the memory segments and make sure you all are clear on the 3 distinct categories. So the memory segments are. We'll start with local, arg, this, and that. These are all going to be indirect. That is, there's a memory location that indicates where the segment starts. And these memory locations are actually given their own labels. Just like SP is 0, we get local is LCL, and that happens to be 1. Arg is going to be 2. This is 3, and that is 4. So what is it that needs to happen if you're doing an access to one of these things? Well, because you're doing indirect addressing, okay, there we go. Because we're doing indirect addressing, you're going to have to use the little indirect addressing block here to figure out where the segment starts. Instead of doing it with SP, though, it's going to be with the corresponding memory register that gives the offset into that segment. Instead of at SP, I'll have at LCL, at ARG, and so forth. Okay? So that gets you that indirect addressing. So let's say you're doing a push, right? What you're going to need to do is begin by calculate actual memory origin. When I say memory origin, what I mean is that when you're doing a push, you're copying something from memory onto the stack, right? So before you do anything with the stack pointer, you've got to figure out where is this thing coming from, okay? Now, We made reference last time to the fact that looking at our memory map, there we go. We had 0 to 15. You might remember that 13 to 15 are yours with which you can do whatever you want. I'm just going to give a friendly suggestion that you might, after calculating that memory origin, stash it somewhere safe. Maybe you'll find a cleverer way around this. Just know that I didn't. Okay? You got to figure out where that memory origin is, and then you may have to stash it somewhere safe. Okay? All right. So now that you've got it stashed somewhere, or maybe you can just get into A somehow. There might be a better way to do it than what I did. I stashed it somewhere safe. So now you need to copy that value into D, right? And at this point, you do a push, like with your constant. You know? So that's an indirect push. An indirect pop will be similar in that you still have to calculate that actual memory destination. You may find it helpful to stash it somewhere. This is the sort of thing that before you even write the code, it's worth working out on paper what the assembly language is even going to look like. Right? Get that as clear in your head as you can. You can even write some assembly programs and test them out and make sure they do the right things. Okay? And so that's the indirect. Now, relatively easy is pointer and temp. And what makes these easy is that you can directly calculate the source or destination address at translation time. See, for the indirect, this calculation is going to have to be ASM code that you generate. Okay? There's no alternative to that. For these, you can calculate ahead of time. Here's what I mean. You know that the base for pointer is 3 and the base for temp is 5. So if I have push pointer 3, or no, I'm sorry, push pointer 1, then I can directly generate code that goes, does an @4 and does things from there, right? D equals M and life goes on. I don't have to calculate that offset at runtime. On the other hand, if I'm doing something like push local 3, well, in this ASM code, I'm going to have to be adding 3 to something, right? And that something is the memory location that's indexed by LCL over here. So you need to think carefully about how those pieces fit together when you're working on the memory segments. Cool. Any questions? Any questions? Yeah.
When I say push constant 3 and push local 3,
Yeah.
what's the difference between those two instructions?
Push constant 3 says push the number 3 on the stack. Constant isn't really a memory segment. Push local 3 means find the fourth memory location in the local segment, copy its value onto the stack. Push is how we get values from memory so that we can do math. Pop is how we store the result of the math back in memory.
Sounds the opposite from what usual push and pop does. Pop stores,
Yeah,
push removes.
copies.
Okay.
And really, even pop is just copy. Pop is copy and decrement the stack pointer. So the value is actually still sitting there on the stack. In principle, you could use it. Would that be insane? Of course it would be. Why? Because it can be overwritten by another push. But it's not automatically destroying it. It's just sort of setting it up to be destroyed. Any other questions? Any other questions? All right. So I'm going to warn you ahead of time. I'm not around very much tomorrow. I've got several off-campus things I need to do. On my calendar, I'll be pretty findable between, say, 9:15 to 10:45 tops. But I have to be at an off-campus appointment by 11. So kind of the mid-morning will work. And then late afternoon after my 150 lab is over, like 4 to 5 tomorrow, I should be around. Just giving you a heads up in terms of what my availability is going to look like. Cool. All right. Happy virtual machining. On Thursday, we're going to begin going over the next phase of the virtual machine translator, jumps and functions.